So let's start. Today's speaker is Professor Minwoo Suh from Gumo Technical University. He was our former member. Actually, he spent 2 years from 2015. Okay, so we're very happy to have him as a speaker today. So he will today talk about some supergravity. Please start.
Thank you for inviting me, and thanks for organizing seminars for video. Thanks for having me here. And it's always good to be back. And I just entered the gate, and I didn't even look at all the buildings. My feet was leading my way to the seminar today. So thank you so much for having me today. So today I will talk about recent development with some interest people have in the field of supergravity and relevant. And I will discuss these things. So I will introduce some backgrounds of the topics I will cover, and then I discuss some supergravity solutions, and then I will present 3 rules to calculate the observables from the supergravity solutions. So it's much better. But the thing is, I have planned maybe too much. So schematically, I have like a 10 minutes for each topics. So I will be kind of brief. And I tried to choose a Blackboard talk today. So I may not be able to present you details of the calculations, but I hope that I can tell you about the moral of the story, the key points of the story. Hopefully I can deliver those things to you. So I think that is a good thing about the Blackboard talk. Hopefully it can happen today. So this is the topic today. And what I'm gonna tell you about is 3 rules to calculate observables in supergravity. And 3 rules, before that, let me tell you observables. And mainly observables I will calculate are these things. So these are like first rule. This is for the SCFTD, and these are 3-dimensional and 4 dimensions, 5 dimensions, and 6 dimensions. So these are 3-dimensional SFTs and 4, 5, 6 dimensions. So each dimension you want to compute some observables mainly interested in. They are in 3 dimensions case. This is due to ADS 4 solutions, 5 solutions, 6 solutions, and 7 solutions. So the thing is, in ADS 4, you want to compute free energy. And in 4 dimensions, you want to compute central charge of the 4-dimensional superconformal field theories. And 5 dimensions, again, it will be 5-dimensional free energy. And 6 dimensions, you again have central charges. So these are the main observables I'm gonna tell you about. So don't worry too much about it at this point. And 3 rules. So what I'm going to do basically is I'll introduce you supergravity solutions first, and then I'll tell you 3 rules to compute their observables in 3 different ways. And the 3 different ways I'm going to talk about is, the first one is extremization. And second one is gravitational flux. And the third one is the most recent one, equivariant localization. And you can systematically and mathematically compute observables, not by computing on-shell action of the supergravity solution, but you can go into the structure, mathematical structure of the solution and compute it from a systematic and mathematical way. And the first one is the extremization, and they are gravitational dual of C extremizations, F maximizations, and those computations in field theory. And they usually introduce some kind of master volumes and then extremize them to get the observables you want to compute. But this is the one I'm not going to talk about much today. And I will concentrate on the second and third ones. And they will be presented in the third and fourth part of my talk. Okay, so this is the basic plan for today's talk.
Can I ask a nice
Yes.
question?
Yes.
So you mentioned observable, but why do you consider free energy for other dimensional superconductor field theory and central charge for even dimensional?
Thank you for asking. I think mainly they want to compute central charges, but central charges are not defined in odd dimensions, so they compute free energies instead. And for even dimensions, you have central charges for each dimension. It's like A is the famous four-dimensional central charge. Or they also have a C central charge, but in holographic theories, A and C are equal. So you can tell you compute A or C, and similar story goes to.
For free energy also makes sense in even dimension.
I think so. Yeah, that's another question. Okay, so let me briefly tell you, starting with the recent solutions, and then I'll tell you the mathematical and systematic ways to compute the observable. Okay, so let's start from one backgrounds. First one is the topological twist. This was done by Witten and Gaiotto, 2009. So topological twist is a way to preserve supersymmetry on a curved space. And it was first introduced by Edward Witten in the 80s. And then one of the famous use of topological twist is done by the Davide Gaiotto to get six-dimensional 2, 0 theory and get the class S theories in 4 dimensions. And this is very standard way to preserve supersymmetry on a curved space in the field theory and likewise in the supergravity. But recently, this kind of Suji preserving method was generalized in some sense in the supergravity solutions. There is another thing I'm going to tell you more about. But here I'm just mentioning these things as a background. And the second background I'm going to tell you is recent development about black hole microstate counting. So this was done by Benini, Christoph, and Giaffaroni, 2015. So what they studied was these black holes. ADS 4 black holes, and they have horizon geometry, ADS 2 horizon geometry, ADS 2 cross Riemann surface. This is the horizon, and this is the asymptotic area of the black hole. And they are magnetically charged. black holes. So if you compute the Bekenstein-Hawking entropy of these black holes, they can be obtained by topologically twisted index of 3D ABJM theories. So it was thought to be quite an achievement because you can microscopically count the black hole microstate by using ADS-CFT dual computations, and you get the precise match between the Bekenstein-Hawking entropy and the field theory partition function. And this was also generalized to ADS-6 black holes, ADS-2 cross some Riemann, and you can get the Bekenstein-Hawking entropy of this 5D cyborg theories.
I have a question. So do you think the index fully capture black hole microstates?
Fully, you mean quantum mechanically or perturbatively, non-perturbatively?
For example, I think that, for example, cohomology in index we have some alternating sign. So
Oh, those questions I see. So I think, yeah, I didn't say about, and Juno is here, but I'm only talking about static magnetically charged black holes, and there's another class of solutions, electrically charged, rotating black holes, and there's different class of black hole solutions, and they may be relevant for your questions like alternating signs. And yeah, this is quite different development. So you have two classes of black hole solutions. One is the magnetically charged static solutions, and another one is electrically charged stationary solutions. And their black hole entropies are computed by the superconformal indices and the thing you mentioned is shown up. So these are the previous examples. I'm just mentioning previous developments. And recent development after these things is this. So people has done these computations, and then they came with a new class of solutions. They are like this. So you used to have a Riemann surface as a horizon geometry, ADS2 Riemann, ADS2 Riemann, and here it's rotating. But here now you have a horizon with orbifold. So now you have some orbifolds on the horizon, and they found precise solutions of these kinds of black holes. So these are ADS4 black holes, but on the horizon you have orbifolds. Why are they interesting? So one of the examples is the spindle. So these are a kind of orbifold, and I'm going to tell you in detail what it is. But the thing is, what is this black hole? This is precisely this black hole. Magnetically charged, accelerating black holes. So far you have been studied the static magnetically charged and stationary electrically charged, but people has begun to study magnetically and also accelerating black holes. So what are these things? So these are a class of Klebansky, Demiansky classification. You have accelerating black holes, and these are the examples of the orbifold horizon black holes. And you also have a different orbifold. The example is this, ADS7, asymptotically ADS7, but you also have a horizon with the orbifold. At this time, the orbifold is called the disk. in this case. And what is interesting about this case? In this case, this ADS5 gives famous field theory, supercompound field theory, four-dimensional RGRS Douglas theories.
So this one is not black hole.
Oh, this one, yeah. This is you may call the black brain, some kind, yeah, because it's not ADS2. Usually ADS2 you call black holes, ADS3 black strings, and ADS4 and 5 you may call it black brains. Yes. So these are the background I want to share with you. And let me move on.
And why OV folding appears? Is it done by hand or?
Oh yeah, that's what I'm gonna tell you right now. Second part. So this is done, and let me move on to the.
Could you explain more about the difference between magnetic and electric black hole in this setup? Or why isn't there electromagnetic field?
Right, very good. So here, here, ADS4, asymptotically ADS4 with the ADS2 horizon is a magnetically charged, right? But in 4 dimensions, you have a electric magnetic duality. So here you can turn on electric charges. So you can make it ionic. But still, it's different from this class. So here you can turn on and make it ion. But here, can you turn on magnetic charges on rotating black holes?
I think I didn't see it.
I didn't see it either. Yeah. So the answer is there are two classes of solutions. In this class, magnetically charged, you can turn on electric charge. Here, you haven't seen those things.
Is it abelian theory or another?
Yeah, they're all abelian. That's what I'm gonna tell you too. So let me move on.
Okay, one question about the magnetically charged black hole. So can we, so there exists also some half BPS and quarter BPS, that kind of BPS black holes in the magnetically charged case?
Yes.
So in other words, in the ADS space, rotation is not necessary condition to make BPS black holes. Is
That
that
is
right?
true. That is, I agree with you. So you don't have to turn on rotation to have a BPS black holes.
Okay, thank you.
Thanks. So let me quickly move on to the second part. So here I'll just tell you local form. You want to see the form of those black holes? So I'll just give you an example of so this is the example of ADS 5 cross spindle solution. So the metric, so this is a solution of second dimensional gauge supergravity with the I goes 1 and 2 means U1 sphere gauge. supergravity in D equals 7. So this is a 7-dimensional solution, spindle solution looks like this. So the thing is, you have a metric solution just like this, and you have two U1 gauge fields here, I1 and 2, and two scalar fields, x1 and x2. And the functions are here, and they are all functions of this y coordinate. So this part is the spindle part. This is ADS5 cross spindle solution is like this. Then let me tell you more detail of this solution. First of all, I just said local solution of this, but you want global completion. What I mean by global completion is that depending on your choice of parameters and range of the coordinates, it can be many different solutions. It's not just the metric. So it may represent many different solutions, but you have to fix coordinates and parameters. And one way to fix the coordinate and parameters is that you solve for qy0. This is q function, and q set it to 0, and you will find y1, y2, y3. Because this is cubic equation, and you fix the range of the solution to be y2 to 3.
P is quatic. It's H1 times H2 and H quadratic, which is quatic equation.
Oh, it's quartic. Okay. But okay, let me forget about the number of solutions. Anyway, you pick two solutions and you make it the range of the solution to be like this. And then you will get a what's going to happen is this. And then what they mean is this part. If you approach y equal y2 and y3, the range of these coordinates, the metric will be written in this way. So if you approach these two coordinates, and then after some computation, you will end up with this. And then if you fix this guy to be like ki squared is 4yi. You introduce this kind of integers, n plus and n minus, and then g coordinate becomes orbiform.
So what was the definition of K1 from this variable you defined?
Which I don't want to use some relation we don't need.
I see.
And then after computations, you end up in this shape. And the important thing is it will be like this: dg squared over n plus minus squared. Right? So this part is kind of orbiform by these integer numbers. So it becomes periodic coordinate. And the period of delta g is delta g, and so these are orbiform numbers.
delta G is just some number.
Yeah, that's some number.
So do we need some boundary conditions to get the regular geometry?
Yes, these are the boundary conditions you're fixing at this point.
Mm.
So what's going to happen is just like you said, it is topologically sphere, but you have two orbifold points. Like this. So here, like n minus n plus two orbifold points. So this is the shape of so-called spindle solution. So this is why this metric is called the spindle. You have two orbifold points at the North Pole and South Pole. And I'm not gonna do the same. Yeah, okay. And then move on to the fourth part of it. And then you compute the Euler characteristic of this spindle part metric. How you do it is just do the Euler characteristic formula, R sigma or sigma. You just do this computation. Which scalar volume form on the spindle metric. And then what you get is this. So after a very complicated computation involving Ricci scalar and volume form, it end up with a very simple answer, just like this. And you can also do another computation, flux quantization. So you have two U1 gauge fields, and you do the flux quantization just like this. And then you will get Ti, an integers. And then P1 plus P2 is going to be like this too.
Sigma integral range is this interval y2 to y3.
Sigma, you mean this?
Yeah.
Oh, sigma means it's a symbol for spindle.
For finite interval of y, on your left there is a box for the y range. You said the y range is.
Oh yeah, yes.
That region is causally disconnected from outside, or
Yeah, outside you just ignore. There's no space existing outside.
geodesically complete.
Yeah. Just this range is already enough. And you ignore the other part of the solution. Just take this one. And then you will see this example. And you can do also similar computation for disk. Disk is, in this case, spindle, you have two orientiforms. But disk solution, you only have one orbifold point at the center. So this is the singular one. And then you compute the, and let's say that orbifold number is L, and you compute the Euler characteristic, and what you get is 1 gram. So this is a brief introduction.
What is the meaning of one?
Oh, Q1 and Q2, they are free parameters. Yes. Sorry, I just
So then what is the meaning of one?
Q1 and Q2, they are free parameters, numbers, and they are actually magnetic charges. Some sort.
What is P1 and
Oh, because these are functions of Q1 and Q2.
Ah.
Yeah, sorry. Yeah, that is correct. Yeah, you've been following, yes. So these are eventually functions of Q1, Q2, n plus, n minus. So everything will be expressed in terms of Q1, Q2 magnetic charges and the orbifold. So these are from the metric and these are from the gauge. this computational system. So these are brief introduction about the spindle solution and disk solution. It has been studied recently, some of them. And basically, spindle solution is a OB4 geometry with a two OB4 points. Numbers are plus and minus. And if you compare Euler characteristic and Fox quantization, you get these simple structures. And disk solution is a geometry with a singularity at the center, and you get very simple Euler characteristic. So and there are black holes having this in the horizon. There is one. Okay, let me then move on to the next part. What I'm going to tell you from the next part is more general than these solutions. These solutions are just the examples, and the method I'm going to tell you to compute the observables from now on are much more general than these solutions. They can apply to more general situations, and I'm going to tell you. So, number 3, gravitational loss. So what are the gravitational blocks? It is a method to compute observables in a systematic way. And I'll briefly tell you how you can do these computations. So the name of the gravitational blocks are analogous to field theory holomorphic blocks. So in field theory, like some index computations, you end up with some holomorphic blocks, classical holomorphic blocks. They are like two separate blocks, and you can decide how to glue these blocks together, and the answer will give you partition function in the field theory computations. And analogously, you can do a similar procedure in the gravity, and they are called the gravitational blocks. And I'll tell you, so these are CT. Analogy. And the thing is, gravitational block is not a derivation of observables. It's just a conjecture. So you just conjecture something called the gravitational blocks, and you can use it to compute observables. And I'll just show you an example. So let's move on to the gravitational blocks. So what I've written down here is that this is the observable. You want to compute. And just like I have told you here, block, you mean you have two blocks and you glue in some way, and you will get the observable. So these are the blocks. So curly F, they are the blocks. And then you have to choose how to glue them together. So plus or minus. So it's a way of gluing determined by the sign between these two blocks. And then you go to this parameters. So you can define phi I constrained by this kind of relation. And delta i's are fugacities of abelian R symmetry. And n i's are magnetic charges. And n plus minus, they are orbifold numbers. And this quantity is the rank of global symmetry groups. So I is 1, 2, 3. Delta i's are fugacities of abelian R symmetry. I'll tell you more about it. And this n, bold n is a magnetic charges, which I wrote down as Q1 and Q2 or P1 and P2, some kind of posting. And n plus minus, these are the OP4 numbers I have introduced for the spindle case. And this case, OP4 numbers. And currently D is the rank of the symmetry group, just like this. So, and you introduce some parameter, phi I, constrained by this thing and this thing. So this is the called first condition. And this is more like a flux quantization. You may remember this like flux quantization issue.
And what is about phi I?
R phi.
Yeah, phi.
What is phi?
Yeah.
Phi is just a parameter introduced by imposing this constraint. So this is quite conjectural structure. But yeah. But I'll tell you how to use this and that will convince you about this structure.
These are the free energy of CFT.
Yeah, that's what I'm gonna tell you right now. So I have written down a system of equations to compute observable with the gravitational blocks. And I have already written down the shape of the gravitational block here in each dimensions. So these are conjectural structure. So you propose in 3 dimensions, like ABJM theory, you have a gravitational block look like this. And 4D, you have this, like and for 4 super Youngians, you have this shape. And 5D, like a 5-dimensional cyborg theories, you have this kind of gravitational block structure. And 60 two-comma theories and their variations, you have this kind of block structures. So you can take this part and you plug in here and here, and you constrain these fugacities by these computations, and then you do extremization, and you will get the free energy or central charge in each dimension as you wish.
So, but for each block, what is the corresponding geometry? For 3D, is it 3 sphere?
Yes.
Yeah, and for 40 and 60, you use S4 and S6 as geometry corresponding to the block.
Yes, I'll tell you in the process of examples. Yeah. Okay, then let's just do the example, and you will be much relieved. So let's do the example here. So the example I'm gonna take is this. It's this case. Equals 6 case. And then you will choose F minus here. And write down 1 over epsilon. And the shape of the graph is this. B6 come out. And it is something like something squared, because delta 1 and delta 2 squared minus something squared like this. And then here you plug in I didn't write this. So phi I is given by one is given by phi I plus mi epsilon. This is I think you can. So you just plug in here phi 1 plus m1 epsilon, phi 2 plus m2 epsilon, phi 1 minus m1 epsilon, phi 2 minus m2 epsilon. And then you do the computations, algebra, and 2 phi 1 plus m1 phi 2. And 1 and 2 epsilon squared plus phi 1 phi 2. So you just expand these expressions and you end up with this after simplification.
Are you doing CFT computation or gravity computation?
This is a gravitational computation. Yes.
Where do you get all these functions?
Oh, yes. So just like I said, these are conjectured structure you can impose on the gravitational solutions. That is gravitational fields. And then you go to equivariant localization and you derive these things from the bottom, all the way bottom, from the Einstein gravity.
Oh,
Yeah, that is the equivariant localization. So you just impose gravity's theory, and then you do equivariant localization, and you end up with these things, structure shown. But at this level, people didn't know about this mathematical foundation, and they just imposed the structures, and they used these computations, and they found that it works to find the observables. So anyway, you find this, and then you externalize this. And then you find epsilon star is something, phi 1 star is something at the fixed point. They are all functions of n plus minus n1 and 2. And so on. And then you plug them, the extremization values, you plug them back into the gravitational, observables. And then you find something like this, and I'm not going to write down all the details of it. And this is the ADS 5 cross spindle. Central A. This is to hold the CFT, and it has a central church, and this equals a. So what I'm saying is you do the extremization and you get the observable at the extremization value, and you recover the central charge of ADS5 space of this chip, ADS5 times spindle, and this is 0 to 40 SFT, and you can compute the A central charge of 4-dimensional SFT by doing these computations. Then let me move on to the next one. So one way to compare observable, not computing by on-shell action of the supergravity solution, but from some systematic way, was introducing these gravitational blocks and extremizing the observable. But it was kind of conjectural structure. But recently, people have found that you can actually derive these things from the first principle in the gravity theory. And that is called the equivariant localization. And I have to do a little bit mathematical introduction to this topic of the equivariant localization briefly. So what you want to have is compact Riemannian manifold with a metric G of dimension 2n. Think about compact Riemannian manifold and even dimensions 2n. So you have a manifold metric. And you have a U1 isometry. This is the killing. And then you introduce finally equivariant, something equivariant. So what you have to do is equivariant differential. It is called the xi, and you define this by this. E minus and what is this? This is just the normal derivative in the differential geometry. And is this? This is internal product. So you can write it in this way, but sometimes you write it this way. Like Nakahara, you find it in this way. And what does it do? Right? It does it this. If you apply x and y and you take internal product with ex, what you get is
UI.
yes. In this case, you don't have overlapping component, so it's 0. And IEX BG dx is minus 3. Like this. It's a way of dealing with the contraction in the differential geometry. Yeah. Anyway, you introduce this guy here and define equivariant differential in this manner. And then the thing is, if you take this 2 times, you end up with a minus of 3 derivative. So that means you can define space of invariant polyforms. Let's say polyforms are this capital phi, and they are zero if you apply this derivative to the invariant polyforms, equivalent invariant polyforms will be zero. So D psi is a nilpotent, and this gives you construction of equivariant homology. So from this, you can define some structure of equivariant cohomology introduced by these equivariant differentials. And then I have to introduce you Berlin, Bergen, Apia, this point, formula. So if you define some polyforms, which is null by this operation, you can do the integration of these polyforms, and you will get a fixed point formula. This is what we are going to use heavily. I'm going to write down formula because it goes on and on and on. So what I'm doing here is you have these polyforms, capital phi, and then you can do the integration of this using this fixed point formula. What does it mean? What I mean is, let me explain the formula a little bit. So psi here, the killing vector here, can be expressed by this. And then normal vector n to f. Explain. Okay, so if you have a killing vector here, you can write down the killing vector by coordinates with some parameters we introduce in the killing vector, so epsilon I. So these are the epsilon i's showing up in this formula. Killing vector parameters. They are epsilon 1 and n here. And then normal bundle to n. So here f is the fixed point. F. Or fixed surface and so on. Something, yeah, corresponding to fixed point. And then some normal bundle to fixed point. Let's think about manifold M as some fixed point. And then you can think of normal bundle N to the fixed point, and you can break it down by the line bundles L1 to Kn. Each of them is rotated by the component of the Killing vector. And then this fixed point is dimension 2k. And the whole manifold is 2n, dimension 2n. So you can subtract 2n minus 2k, actually that is the dimension 1. Fixed point, 2n minus 2k. And then this normal space will be like this, Riemann divide mod out by gamma, and then it is the degree of this finite group is called this df2n minus 2k, and that is what you see in this form here, and this guy should appear, and so on.
Why is the fixed submanifold always even dimensional?
That is the limitation of this formula. It doesn't have to, oh, the fixed point to n. Yeah, I'll tell you more about it, hopefully. Yeah. So let me just tell you on the
What
example.
is phi 0? I know.
Oh, phi, thanks for asking. So they are polyforms. And phi 0 is 0 form, phi 2 is phi 2 form, and so on. So polyforms, phi is like a 0 form plus 2 form plus 4 form plus and so on. Polyforms.
And what the definition of the integration? Are you saying that you want to choose the top form?
Yes, top form.
You mean that top form fixes all lower order forms?
Right. I'll show you one in example. I think the plan is I'll show you the simplest example here, and then I wrap it up, and then I just briefly go over supergravity by telling you, and then finish. So just to show you one example, and you will be much more convinced.
But I mean, it's very weird that the product of the component of Killing vector appeared there. It doesn't look like you have a general covariance.
I see. I don't have it. Yeah, let's come back. So let's do example S2. The simplest example, and you will see how this machinery works for the simplest example. So actually, how does it look like? And theta is like it looks here. The range of the coordinates are like this. Okay, then Killing. Okay, just like here. We define Killing in this way. And then sphere, two sphere, you can think of it as topologically you have two fixed points by introducing this coordinate, North Pole and South Pole. Okay. And then you can define, just like Taiwan said, that is very important. The top form fixes the rest of the structure. That is quite right. So you have to define polyform here.
Isn't it opposite? I mean, the lower forms in the polyform completely determines the integral of the top one.
But let's see how it goes for this example.
Possibility.
So you construct polyform here. And then how do you do that? You choose this to be the top form, two form, because this is 2 dimensions, two form is top form. And you introduce this scaling vector parameter, 1 over b here. So this is the top form, two form. And then how do you write it down? This is sine theta, d phi, right? And then you add something here, and then it has to be 0 when applied by the equivariant differential. It should be 0. So and I'll tell you the answer. The answer is that you put cosine theta here.
0 form.
Yes. So 2 form and 0 form, and 0 form is cosine theta. And how do you know that? You do this computation and do this. This is d phi minus phi, right? So d applied to volume form, what is this? 0. And d applied to cosine theta is sine theta. And then you apply inner product to the volume form. And d cosine is phi, so you root this part, and you get the sine theta, d theta. And because you don't have 1 over b, because you have this right here, so b and 1 over b cancel out, and you lose this part, and sine theta, d theta is what you get. And you apply inner product to the scalar, and what is inner product of the scalar? 0. Because scalar doesn't have any coordinate component, so it is 0. So this is what you get, and this is 0. Right? So this is the right choice of the polyform for the two sphere. And then you come to this equivariant localization formula, and let's erase this and do this here. Now, you don't want to compute this. You want to compute the volume of the polyform, and then like this. Top form, the integral is defined by the top form, and this is. And then we use this formula. Let's do this. So here, it is 2n, 2 dimensions, right? So n is 1, right? 2n dimensional n equal, and this is 2 dimensional n equal 1. So it's like a just epsilon 1 only, and 2 pi, right? Oh yeah, and before that, you have to introduce this, these things, and you define like this. So these are the killing vector parameterizations, and at the north pole, you define it to be plus, and south pole, you define it minus. So this is conventional you need, and this is what you need to accomplish your job. So let's say this is n plus 2 pi, and pi 0 is here. Pi 0 north, pi 0 south. Like this. So you just use this formula, epsilon 1 to n, but only 1 epsilon is here, and 2 pi is here, and phi 1 north, phi 1 pi 0 south. And then 2 phi, and phi 0 north is phi equals 0, and phi equals 0 is cosine 0 is 1. So it's 2 phi times 1. And epsilon north is plus b. Plus 2 phi 0 at the south. phi 0 is this guy, and at the south is cosine pi. Cosine pi is -1. And at this time, epsilon south is -1. So you end up with the E 4 pi. And this is what you know for the volume of the two sphere.
So for filling back, you need two coordinate pairs, north and south.
Right.
But for polyform, you need only one. Just you don't need to divide.
Well, you don't need.
Why? I mean, that's what I'm hoping.
I think the point is the calculation according to this fixed point formula should be sum over fixed point.
Right.
And we have two fixed points. And so I think the related question is, since you have to choose that epsilon north and epsilon south in that specific way.
Right.
Then why?
Yeah, so and my question was about that, and why should I make that choice? And now I realize that question is actually.
Okay, then let me briefly. I have to finish. So let me move on. So the thing is, this is two sphere example, but you can do S4, and also you can do CP2 case, and you can do CP2 case and look at the Gibbons Hawking paper. They define nuts and bolts. So nut is 1D fixed points, and bolts are two-dimensional fixed points. So 1D fixed point part for the CP2, you use this part of formula, and you finally have a two-dimensional fixed point in the CP2, which is called the bolt in the literature. And then you have to use this part. The fixed point is 2 dimensions, so you have to introduce this part to compute the volume of the CP2 using this fixed point model. So there are examples using higher dimensional fixed points in the solutions of the gravity, like the CP2s and so on, nuts and bolts and so on. So this is the formula you use.
So why do you call it localization?
Because I think because you concentrate on the fixed points, and then it gives you the whole. Yeah, it's a fixed point formula. You have a geometry, and with the fixed point, you can use this formula to compute them. And you can apply for the spindles too. So probably two spindles with the two fixed points, which are not these singularities, they are all before single fixed point, and then you introduce all before numbers in this. I cannot show you this. So let me wrap it up today, and I cannot tell you the details of this equivariant localization in the supergravity. So you can use this formula in the supergravity, and then you end up with the gravitational blocks I have shown you. And I cannot tell you the details, but let me just briefly tell you the story and finish. So let's say ADS 7 case, 7-dimensional action. And you take the answer of ADS 5 on some 2-dimensional manifold. And then you will get 2-dimensional action. So this is part 6 in supergravity. So dimensionally reduce the 7-dimensional action to 2 dimensions, and on this answer, ADS 5, so you lose ADS 5 part, and you end up with a 2-dimensional action like this. And then you can write down, and you get the equations of motion. And you apply that to the action. And if you fully apply equations of motion to the action, it will be on-shell action. And it is already on-shell action. And nothing interesting. It's already fixed. You have no freedom to extremize, and you already get the answer. But it is no fun. So you partially impose equations of motion. So partially on-shell action, you write it down. Partially on-shell. So let me write down one example. Partially on-shell. I'm sorry, I cannot explain the language of this. Something like this. So scalar potential, volume form, gauge fields, and so on. And then what you do is you use Suh variations to get the BPS equations. And then you apply these things, and you use this to construct polyforms. Fine. So you're just following this example.
From killing sphere.
Yes, killing spinner, bispinners. You construct polyforms using the bispinner method of supergravity, using BPS equations. You construct polyforms just like this. And then you do the integration of the polyform using this fixed point formula. And then you will find some polyforms given this. Is partially on-shell action. And I'm just telling you the overall story, I don't have time. And then in the process, you find the structure of the gravitational production. Like this was. This was for the alien case.
From component of polyform become.
Yes. Yes. So it begins with this, and you will find that this is a part of the polyform in this computation. And then if you reduce this using this polyform structures and so on, you end up with a gravitational block structure shown. And this is kind of derivation of the gravitational block from the first principle of the actions, just using it for form.
The polyform nodes is partially on-shell action.
Yes, this is actually part of the polyform. Part of the polyform. You dimensionally reduce it to 2 dimensions, and you write down partially on-shell action, and then you see this is already polyform. Actually, this is 2 forms. So it's volume form, 2-dimensional volume form, and this is 2 form here. So it's a 2 form part of the polyform is already given by the on-shell action, 2-dimensional. And then you use these structures and so on.
I mean, normally BPS equation is stronger than equation of motion, but you need some something like Gauss constraint or
Right.
because BPS equation lacks such a equation, you don't get fully on-shell action.
Right. But we don't even use all the BPS equations. I think you take whatever you need to construct the polyforms, and yeah.
But polyform is on-shell. It satisfies killing 스피너 있기전. You can
Yes.
drop it from.
Right. So you apply part of the equations of motion, and you apply something that satisfies these equations, and you can construct the structure just like.
And so if it's fully on cell, it should be total gravity.
Yes, you can show. You apply all the equations of motion, not this, you get just simple answer. One total derivative action, which is volume of the space. So that is, all fixed and you already visualize. You don't need this one. Okay, so this is the end of the talk, and let me just summarize some open questions. Open questions. The first thing that, of course, are dimensions. You see, key 6-point formulas you have already pointed out. This is only for 2 even dimensions, and you need localization for the odd dimensions. And yeah, I think concerning this matter, this is fun. And the other things I refrain from. Thank you for